Okay, let's dive right into this. Welcome to our explainer. Today, we're stepping right into the middle of what might honestly be the greatest cosmic detective story of our time. It's a mystery that's baffled the absolute brightest minds in astrophysics for decades, and it fundamentally challenges how we understand the very fabric of reality. We're looking at the ultimate missing persons case, but, well, on a galactic scale.
Just think about everything you can see. The stars, the planets, the dust, you, me, literally everything. According to our current standard cosmological model, all of that normal matter makes up only about 5% of the universe. Just 5. Meanwhile, an absolutely absurd 25% of our entire universe is supposedly made up of a completely invisible substance. So that brings us to the massive hook for today. Are we relentlessly searching for this invisible ghost that somehow makes up a quarter of reality? Or is the ultimate plot twist here that this invisible substance doesn't exist at all, and actually our fundamental laws of physics are just plain wrong? Now, you might be wondering, why does this matter to us? Because the answer is literally going to rewrite the textbooks on how the whole universe operates.
Part 1. The Missing Mass Mystery. To really wrap our heads around this, we need to head to the scene of the cosmic crime. Here's the glaring mismatch we're dealing with. Einstein's field equations of general relativity, they work perfectly in our solar system. They hit the nail on the head every single time. But when you plug the visible mass of a galaxy into those exact same equations, it completely fails. The actual observation is that galaxies are rotating so fast that they should literally rip themselves apart and fling their stars out into the void. They somehow have way more gravity than they should, based on what we can actually see.
Section 2. The prime suspect, dark matter.
So faced with all this missing gravity, the scientific community had to come up with a solution. Enter dark matter. It's proposed as this exotic, invisible mass that produces gravity but simply doesn't interact with light or really any electromagnetic forces. The model basically suggests that the visible galactic disk actually sits at the center of a much larger, much more massive and round halo of dark matter. Picture, a tiny glowing dinner plate suspended inside a massive invisible beach ball. It's the gravity from this vast, unseen halo that supposedly keeps those rapidly spinning galaxies from just flying apart.
And this brilliantly illustrates why dark matter became the gold standard for astrophysicists. It's really not just a blind guess. It successfully models some incredible phenomena. It fits the thermal radiation patterns in the early universe, the afterglow of the Big Bang, called the cosmic microwave background. It explains how light bends or lenses around immense galaxy clusters. And in super high-velocity collisions like the bullet cluster, it accurately models how visible matter slows down while the invisible mass seemingly passes right through, completely unaffected.
Section 3. Cracks in the case.
But hey, here is where our cosmic detective story takes a major twist. For all its mathematical successes, dark matter has a pretty massive physical problem. Despite 30 years of searching deep underground with specialized detectors, and honestly, tens of millions of taxpayer dollars spent, we haven't found a single particle. It's the ultimate no-show. Furthermore, astrophysicists point out contradictions in the mechanics, like a concept called Chandrasekhar dynamical friction. Think of it kind of like a slingshot. Just like we slingshot space probes past planets, a dwarf galaxy moving through a dense halo of light dark matter particles should theoretically slingshot those particles away, lose its energy, and slow down. But actual observations show these dwarf galaxies just don't slow down as expected.
So the crucial point here is this severe paradox. We observe a really precise, incredibly tight correlation between a galaxy's visible matter distribution and its rotation rate. But we know galaxy formation is a chaotic, messy process full of collisions and mergers. If rotation is supposedly dictated by a massive, separate, totally random halo of dark matter, why in the world does the visible mass perfectly dictate the rotation rate down to such fine details? It's a glaring anomaly that dark matter struggles to naturally explain. And this matters because it challenges whether the whole dark matter concept actually makes logical sense.
Moving on to Section 4, modifying the rules.
Which brings us to the first major challenger. What if we just stop looking for missing mass and instead realize the rules of the universe themselves are the real culprit? This is the field of modified gravity, or MOG. The basic idea here is that gravity doesn't just fade away to zero exactly as Einstein predicted. Instead, at vast interstellar distances, gravity's strength actually plateaus or even increases slightly. This completely universal acceleration law accurately predicts galactic rotation rates using only the visible matter. Yep, no invisible halos required. Now, modified gravity isn't just one simple tweak. It's a heavily evolving field.
It started with a basic equation, sure, but it has grown into complex relativistic theories. For instance, researchers are using models like SVT gravity to explain the early universe, and conformal gravity to predict supernova brightness. They're systematically tackling dark matter's greatest hits, but doing it using only modified mathematics. It's pretty wild.
Section 5. Gravity as an illusion.
But what if tweaking the math still isn't going deep enough? Enter the wildest, most mind-bending suspect yet, the theory that gravity isn't actually a fundamental force of nature at all. And look, this isn't a completely out-of-the-blue idea. It follows a historical trail of breadcrumbs. Back in the mid-1970s, physicists Bekenstein and Hawking linked black hole physics directly to thermodynamics, the behavior of heat. Fast forward to 1995, Theodore Jacobson actually derived Einstein's field equations entirely from thermodynamic principles. Then, in 2009, physicist Eric Verlinde brought the whole shebang together to propose entropic gravity. So what is it? Entropic gravity basically proposes that gravity emerges from quantum entanglement and information theory. Think of a gas expanding to fill a room. That's an entropic force, right? It's driven by statistics and thermodynamics, not some fundamental pulling force. Verlinde argues that gravity acts the exact same way on a massive cosmic scale, just emerging from the statistical behavior of tiny bits of spacetime information. As Verlinde himself puts it directly, gravity is not a fundamental interaction, but an emergent phenomenon. This is a massive shift in how we think. It suggests that just like temperature emerges from the random movement of atoms, gravity emerges from the underlying mechanics of quantum information. Now, what's really interesting about this specific threshold is how insanely low it is. Entropic gravity dictates that when gravity becomes vanishingly weak, specifically below an acceleration threshold of 1.2 times 10 to the negative 10 meters per second squared, it diverges from its classic nature. To put that into perspective, that is 12 trillionths of Earth's gravity. At this tiny threshold, gravity decays linearly with distance, rather than the classic inverse square law Newton taught us in school. So here's how Verlinde uses this concept to essentially replace dark matter. He argues that quantum effects create a positive dark energy in the vacuum of space. At a massive galactic scale, this creates a thermal volume entropy that actually overtakes normal area entropy. In plain English, the vacuum of space itself exerts a sort of thermodynamic pressure. The result is that the extra gravitational pull we observe in galaxies naturally emerges from these thermodynamic laws. No need to invent a single unobserved particle. It just happens on its own.
Section 6. Redefining the cosmos.
So let's step back. We've got our three suspects: dark matter, modified gravity, and entropic gravity. Where does the science actually stand right now? Let's neutrally break down the current battleground. And as you'll see, no single theory is perfect. Dark matter struggles to naturally predict the exact relationship in galactic rotations, requiring unique models for each galaxy, but it performs excellently on the massive scales of the bullet cluster and the CMB. On the flip side, modified gravity and entropic gravity accurately predict those galactic rotations straight out of the box, but they are currently fiercely debating and investigating how to solve the really complex physics of cluster collisions and the early universe.
And honestly, the observational data coming in right now is an absolute tug of war. For example, a massive statistical study out of Leiden Observatory looked at 33,000 galaxies and found their gravitational fields perfectly consistent with Verlinde's entropic gravity. Yet, almost at the same time, a Princeton study argues that dwarf galaxy rotation speeds contradict Verlinde entirely. Meanwhile, observations of the galaxy cluster ABEL 1689 suggest entropic gravity is completely ruled out unless you add heavy neutrinos back into the mix. The scientific method is actively testing these boundaries as we speak, and the outcome will absolutely redefine what we know about physics.
Which brings us to the end of our explainer and leaves us with this final, really profound thought. Are we stubbornly searching the dark for an invisible ghost particle that simply isn't there? Or is it finally time for us to completely rewrite the fundamental laws of the cosmos? Whatever the answer turns out to be, it guarantees that the universe is far stranger and far more fascinating than we ever imagined. Keep looking up, keep asking questions, and never stop wondering about the world around you.